Alex, it's almost time for school. What do you want for lunch today?
I don't know, what are the options?
We have a couple things. We have yogurt, oranges, apples. We have raspberries here, bananas, blueberries. I wonder how many different ways we could make lunch using those items.
That sounds like a job for level 314.
Welcome back, Coding Wizards. Today we're digging into Solving the Genius Square, Part 2, Combinatorics. So what is combinatorics? Simply put, it is the branch of mathematics which formalizes methods of counting. The study really took off in the late 17th century from the work of great mathematicians like Pascal, Bernoulli, and Euler. But don't let the big names scare you. Combinatorics begins with arithmetic you're already familiar with. The so-called fundamental principle of counting, or multiplication principle, states that if you have event A and another event B, then the count of all the different outcomes of the events is simply A times B. Let's use our example of eating lunch, but start with only 4 options: bananas, apples, carrots, and cucumbers. Say we have bunches of each of those, but we're not too hungry, so we're only going to eat 2 things for lunch. How many different lunches could we have? Using the fundamental principle of counting, we quickly see that the number of lunches is equal to the number of options for item 1 times the number of options for item 2. We have 4 options at each choice, so 4 times 4 for a total of 16 different ways we can eat lunch. Here's a look at all those combinations using color-coded squares to represent each food item. This first case is if we eat a banana, then another banana. The case below that is if we eat an apple, then a banana. And this case here is if we eat a cucumber and a carrot. Now let's add 3 drink options, say apple juice, lemonade, and water. In addition to our 2 food items, we'll have 1 drink. How many different lunches are possible now? Well, first we have 4 options for the lunch item, and then 4 options for the second lunch item, times 3 options for the drink. 4 times 4 times 3 equals 48. Another way we could do this is to say that the lunch options including a drink is equal to the lunch options with just food, which is 16, times the 3 drink options. Either method gives us the same result, 48. Here's a look at what those options look like. Now you know the fundamental principle of counting, and it appears everywhere in combinatorics. A common example would be figuring out how many different rolls are possible with a set of 2 standard dice, pictured here unfolded so we can see all the sides. Each die has 6 sides, and we have 2 events. Note, even if we throw both dice at the same time, we consider each dice as its own event here. So 6 possibilities for the first event, and 6 for the second, 6 times 6, or 36 possibilities. Using this knowledge, we can figure out how many genius squares are possible using the dice. Here are the faces of the 7 dice which come with the game, and the first 5 dice all have 6 unique sides, but look closely at the last 2 dice. One of them has only 4 unique possibilities, and the final die has only 2. So the total number of games possible with the dice is 6 times 6 times 6 times 6 times 6 times 4 times 2. And when we do the calculation, we get the answer 62,208. Pretty awesome, right? We just used the fundamental principle of counting to verify and prove the number of games possible with the dice, and our answer matches up exactly with what is printed on the box. To calculate the number of games possible even without the dice, we need to learn a few more tricks of combinatorics. Let's go back to our lunch example, but imagine we only have 1 of each item. That is to say, 1 banana, apple, carrot, and cucumber. We're going to eat 1 at a time. How many different ways can we eat lunch? In the first event, we pick between 4 items. Let's say we eat the apple. Now we're left with 3 items, so 3 for the second event. Let's grab the cucumber. Now we only have 2 choices, so times 2 for the next event, and we'll grab the carrot. Finally, there's only 1 choice, times 1 for the last event, and we grab the banana. So that's one way we could have eaten them. If we want to know all the different ways, we simply multiply how many options we had at each stage. 4 times 3 times 2 times 1 equals 24 different ways. Here they all are. A more formalized way of writing 4 times 3 times 2 times 1 is by using the product symbol. This particular product of all integers from 1 to some value is known as a factorial, and we can write it using this exclamation mark operator. So here we can write 4 exclamation mark, or 4 factorial. If we had 5 items to choose from, we would have 5 factorial, which is equal to 120. With 6 items, 6 factorial equal to 720. More generally, with n items, we have n factorial possible lunches. As you can see, the number of possible lunches is growing quite rapidly. In fact, the factorial function grows significantly faster than most functions you may be familiar with already. Here is a comparison of its growth versus linear, parabolic, and exponential functions. It grows so quickly that out past 7 or 8, it really becomes impossible to chart it with the other functions. Here's another way to visualize it, just compared with exponential growth. It flies off the screen around 9 factorial, and we freeze it here at 10 factorial where the value is already well over 3 million. In fact, you'd need to line up 15 more screens to display how far out it already is. Zooming out here, factorial is the red mark just visible on the far right-hand side. This is not the kind of arithmetic you want to have to do by hand, so let's write some quick Python code to get the job done. Okay, here we are once again inside of Spider. Let's go ahead and create a new source file, and we're going to learn a couple of new keywords today. The first one is def, which stands for define. We use that to define a new function called factorial. It takes here one parameter, we're calling that parameter n, and then we do a colon, and everything we do that is now indented, or every line that is indented, will be inside of our factorial function. We initialize a variable result to equal to 1, and now we're going to use the for loop, which we've already learned, and we'll just say for x in range. We could have started at 1, but we'll start at 2 because 1 times 1 is 1. We'll save ourselves 1 cycle, and here we have to be careful to do for range 2 comma n plus 1 to make sure our loop goes until the very last value of n. Remember, range ends, it goes from values 2 to values less than the second parameter, in this case n plus 1. Okay, now we simply do result equals result times x, and this will allow us, as we step through each time, to multiply the values. When we're done, we want to return, that's a new keyword too, return result, and that allows our function to pass back its result to whatever called it. And here we'll just do a simple print statement to call our factorial, and let's just do factorial 6 inside of our program. Now we can just run it, and of course the first time we run, it's going to ask us to give it a file name to save it, and we'll just call this again counter v2. And we ran it, and sure enough, we got our answer, 720. Okay? This is great, but one thing you should be aware of is in Python, functions like this, many functions like this already exist. So one more keyword that we're going to learn is the keyword import. And we're going to import from an existing library called math, which also has its own factorial function. And we'll just do that one here, math factorial, factorial 6. And this way we can see the result of both our function and the function that comes with the standard library. Now there's some advantages to using the one that comes with the standard library. It's tested. The advantage of using ours is we can do all kinds of things here, our own procedures if we want. We can optimize it somehow if we want. We can put a print statement in here if we wanted. So we can do print result times x, and this will allow, when we run our version, you'll see it'll show each step along the way as it's doing the calculation. Another thing we want to do with our function, we often want to make sure that it accepts the right values, or the right values are passed in. So if we want to do that, we can say here, if n is less than 0, for example, we can raise a value error, and we can put back a response to the user. Simple factorial must pass values greater than 0. Okay? And this would just let any user, or any user of our function, know that it cannot accept negative values. So let's go ahead and run one more time so that the new version is in memory. And then if we do factorial, let's do factorial 10, you can see that works. But if we do factorial negative 10, we get our value error. In fact, it is possible to calculate factorial of negative numbers. I'll put a link in the description to a pretty interesting mathematical journal paper about that. But for our simple case, using positive integers is required. And you can see our function is pretty quick. We've done 10. Let's just do 25, one more. And we can see the values get rather large, rather quickly, but our function works just as we expect it to. Okay, let's go back and learn a bit more, and we can come back and finish up in Python with what we need to do our calculation for the genius square. Okay, so let's imagine you have all 6 items, but you can only eat 4 before getting full. How many different ways could you eat one item at a time? First, you could select from 6 items, then you could choose from 5, then 4, then 3. That gives us 6 times 5 times 4 times 3, or a total of 360 ways. But it would help if we could write this using factorial, and in terms of the total number of options, n, and the total number of items we're going to select, we'll call that k. So here n equals 6 and k equals 4. An equivalent way to write our initial equation is 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1. Notice the 2 and 1 in the numerator and denominator cancel each other out, and that when we do that, we're back to our original equation. Okay, now you should be able to see that the numerator is simply 6 factorial and the denominator is 2 factorial. And here, 2 is the same as n minus k, or 6 minus 4. And now we can rewrite the entire equation using our variables n and k. That gives us n factorial divided by n minus k factorial. In combinatorics, this is known as permutations, sometimes written npk. Let's take a look at what these 360 lunch possibilities look like. This first option represents banana, carrot, blueberry, yogurt. With permutations, the order of the items matters, so if you look closely, you will see those same 4 items in different orders. I'll highlight a few for you, but feel free to look for more. But does the order really matter when figuring out lunch combinations? My mom would always say they're all going to the same stomach, so it doesn't really matter. In such a scenario, we just want to know how many unique combinations there are, regardless of which order they're in. Let's put our permutations formula back up and take a closer look. Okay, so again, permutations will count all the possible orders of any 4 items. What we want is just to know the count of distinct combinations. In mathematics, combinations are often written like this, which you can read as n choose k. To figure out this quantity, we just need to take permutations and divide by the number of duplicates of each option. But recall, we already know how to calculate that. In this case, it's just 4 factorial, or more generally, k factorial. Now we can fill in our equation for permutations, and finally we can simplify, and that's it. The formula for combinations is n factorial divided by k factorial times n minus k factorial. Take a bow. You've just derived one of the most commonly used formulas in combinatorics. Going back to our problem, we have 6 options for lunch and we're going to select 4 to eat. That means we have to calculate 6 choose 4. That equals 6 factorial over 4 factorial times 6 minus 4 factorial. Doing the arithmetic, we get 720 over 24 times 2, which equals 15 possible unique lunches. And here's what those options look like. Now we can bring this all back to our exploration of the genius square. Using our equation for n choose k, we just need to recognize that we have 36 options and we're using 7 pegs to choose them. Let's finish off in Python and create a combination function and use it to calculate 36 choose 7. Okay, let's finish up our code here. So we have a function for factorial. Let's create a function for combination. So remember, we do def and then the name of our function, so we'll call this one combination. And we'll do combination nk, just to stick to the standard math naming conventions here. So our combination function is very simple. We're going to return the factorial of n divided by, and we'll just put this in parentheses, factorial of k times factorial of n minus k. This function exactly matches what we had in our video as we were going through and learning this factorial or deriving this rather combination formula. So I just ran our program one more time and now we can just calculate combination of anything. Combination of, let's say, 6 choose 4. And you see we get the same exact result as we did when we were doing our animation, 15. Notice here though that this has been turned into a floating point number. That's because it's a decimal. And now we can go ahead and figure out our result for our genius square. So remember, we have a 6 by 6 board, so 36 squares, and we're choosing 7 of them using the peg. So we want 36 choose 7, and we get our result, 8,347,680. It's a great result. It's exactly what we'd expect. And now we have a function that we can use to calculate factorials. We can even use this to calculate things like the odds of, let's say, winning the Powerball. What we've learned so far is we can do the odds of, what is the Powerball? 69 balls, and we choose 5. So we do combination of 69 choose 5, and then we multiply that by the last event, which is 26. I believe there's 26 balls in the last slot, the Powerball number, if you will, and we get a result after a moment of, it looks like 292,201,338. So 292 million to 1 are the odds of winning the Powerball. And in fact, we can go ahead and check that. Let's just use Google of winning Powerball. And we see the results from Google exactly match what we've calculated in our program. 1 in 292,201,338. So we've created a useful program in Python, and we can use it for our genius square calculation. Instead of going through 8 million iterations like this loop has done, we've used a mathematical formula to get to the answer much quicker, much more efficiently. And in fact, there are even better ways of calculating combinations, and we'll do that later in C++. But I think we've learned quite a good deal today in Python. We've learned the def keyword for defining a function, import for importing libraries, and our return keyword as well. We're one step closer to solving the genius square. Awesome! So we've made it through the second step in our exploration of solving the genius square. We've learned a lot of new things. We used our friend, the exclamation mark, learning what factorials are. We learned about permutations and combinations. All of these things are the fundamentals of the study of probability. So we've seen again that there are 8 million different games, and now we're ready to begin to figure out how to model this problem so that the computer can solve it quickly. And we think of computers of counting to large numbers like millions and billions, but we're going to solve this problem by only counting to 2. So if you want to find out how we do that, make sure you hit that like and subscribe button so you can join us next time on the next step, part 3 of solving the genius square. And until then, keep taming irrationality bit by bit.